So this is our first I intend to have 3 lectures on Chapter 11, heat exchangers. So we'll cover types of different heat exchangers. There's a lot of them. And we'll talk about the overall convection coefficient used in heat exchanger calculations. Talk about the log mean temperature difference. Hey, that's the same log mean temperature difference that we've already been introduced to. It will be re-emphasized or emphasized again here, but you see that in heat exchanger analysis. We will not get to this today, the effectiveness NTU method, so this will be the focus of today. Let's jump into it. So somebody says I have a concentric tube heat exchanger. That's one of the types of a heat exchanger. So it's like a tube inside of a tube. And so maybe you're trying to visualize it going back like that. And they have maybe some flow in the inner tube, and then you have some flow in the annulus. And a lot of times we would draw the cross section of it like this. And we'd put the inner tube like this. We'd say, okay, the flow inside the inner tube may be going in that direction, and the flow in the outer tube may flow in the opposite direction. It could be, the same direction, that'd be parallel flow, or opposite direction, counterflow. Somebody says, how do they get this to work? Well, often they have an import end on the shell side, and then an X outlet over here. So it's easy to see how they enter and exit the inner tube. But for the annulus region, well, that's how you would do it. So sometimes you'll see a heat exchanger sketched like that. And then what we have here, let's see, this would be maybe the temperature of the hot fluid flowing in. Maybe the hot fluid's flowing in the annulus region. And then the notation would be the temperature of the hot fluid flowing out of the heat exchanger. And then we also have the temperature of the cold fluid flowing in, and then the temperature of the cold fluid flowing out. So that's some notation. I think it's consistent with this. Barely see it, but there you go. Somebody says, I think that's the type of heat exchanger we have is a cross-flow heat exchanger. Well, this is getting a little harder for me to sketch by hand, but I'll try and do a good sense of it. But let's say you have a bunch of tubes. Here I'm just going to show 9 tubes. And I'm going to try to show them in 3D, so the tubes run back like that. And of course they're going to have some sort of header or manifold in which they enter the tubes, so some system by which it's distributed so it can enter all the tubes, as well as collect some manifold or header to collect them on the outlet. But in the tubes, maybe you have the flow of the hot fluid, temperature hot coming in, and then on the exit of each of these tubes, let me just draw it down here, temperature hot out. And I didn't really draw those tubes long enough, did I? Really need to draw them long tubes going way back like that. So that now you can get a sense of what is the fluid that's going to flow across or perpendicular to the tubes. And that would be, in this case, maybe it makes sense to talk about the temperature of the cold fluid flowing into the heat exchanger across the tubes, and then likewise the temperature of the cold fluid flowing out of the heat exchanger after it passes over the tubes. Now, those tubes can be connected or held in place by a bunch of fins. That's often the case. Finning to hold them in place. So you get more and more complicated. Here's an illustration of something. Maybe it's out of the textbook or a different source. So you have flow inside of the tubes, and then you have the cross flow on the outside of the tubes. Here they're bare as shown, but again they could be finned. There's other type of heat exchanger. It's a shell and tube heat exchanger. This is a larger, typically larger, more industrial, could be the size of half of this room type of heat exchanger. So what we have is a bunch of tubes. I'm just going to show the tubes as lines. I'm not going to try and draw the inner part of the tube. That's a tube, and maybe you have, I don't know, 50 or 100 or 300 tubes, and they're held in place by certain plates, right? And so they don't wobble too much. And on one side, you have a cap that has some sort of entrance region so that the fluid can come. Let me try and draw this like this. So that the fluid can come into this region and then enter each of those tubes, but it has to go through the tube. It's sealed. It has to go through the tube. Well, when it comes out the tube out here, it could go into a region where the mixture mixes, and then they have this subdivision right here. And you have a bunch of other tubes on the lower half or the other side. Such that the fluid, maybe I should have changed the color of the fluid, change it to this color of the fluid, going into those tubes. Then it comes out of the tubes, flows around and goes into the other set of tubes. And again, those tubes are held in place. And then they will come out of the tubes, and maybe right in here they have an outlet port where they're collected and flow out. So maybe this is the temperature of the fluid that, let's say hot, that's coming in, and this is the temperature of the hot fluid flowing out. The hot fluid is going through the tubes in the shell and tube heat exchanger. Goes down, collects in a manifold, turns around, and comes back. Sometimes they just have long U-shaped tubes. Actually, each tube has a big bend in it, 190, 180 degree bend, turns it around. Those are common as well. Okay, now, what about the shell side? Well, what you have to have is you have to have some inlet part to it. Let me try and draw it. I didn't pick my color scheme too well, but we could have right here fluid that comes out, and maybe fluid that comes in. You got a bunch of different type of configurations on this. So maybe this is the temperature of the cold fluid coming in. This is the temperature of the cold fluid going out. And it needs to pass over those tubes. Well, as a design engineer, you kind of like the flow of the fluid path to be something like this. Go down, round, down, round, down, around, something like this. I'm just making it up a little bit, but you see the path flowing over. And then you think, how did the engineer make that happen? Well, they introduce baffles or plates that have some sections where it can flow, but not the other section. So baffles or plates. So this would be, as I've shown it, the shell side, and this would be the tube side. Again, there's plenty of different configurations of these. This is what one might look like in the textbook. So here they're showing coming in, the tube side fluid in, comes into this inlet plenum or header, and then they flow through the tubes. Then it flows out of the tubes, distributes again, comes to the outlet plenum, and then out. So here's a shell side coming in, flows, 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 and then distributes out. Okay. Here they have tube sheets to prevent the fluids from mixing and to hold them in place. And this would be baffles to try and direct the flow on the shell side. Well, when you analyze heat exchangers, they like to talk about not only the material that's separating the two fluids. This would be maybe the hot side, and this would be the cold side. And the hot side fluid is flowing over some barrier surface that protects it. Often that barrier is thin, high conductivity material to promote the ease of heat transfer from the hot to the cold. Likewise, you have some convection on the cold side. So we already know how to model this. We'd say, give me the sort of the hot fluid temperature, and then give me the temperature of the wall on the hot side, give me the temperature of the wall surface on the cold side, and then the temperature of the cold fluid at that location where the transfer of heat is going through the system. Okay, and so we would have a resistance, a thermal resistance, and a thermal resistance. Again, 4 distinct temperature nodes and 3 distinct thermal resistances. This would be a 1 over H on the hot side times the appropriate area. That would be maybe on the inside or hot side, different notation. Let's say inside. This would be 1 over HA on the outside. If your tubes are the surfaces, then, and if it has some appreciable difference in the thickness of the tube or from the inner radius to the outer radius, then the area inside is not exactly the area outside. And yes, people would take in that difference in radius into account. Okay, and then what about this resistance? If it's just a flat plate, it would be some L over Ka. But if it was this is a blow up of a section of a round tube, right? And if you're going through this round tube, that resistance would be something more like the natural log of the R outer over R inner, those 2 radius. I think the book uses lowercase r, but you follow the 2 radius, outer versus over inner, divided by 2 pi thermal conductivity of the material, and then that length into the paper, into the 3rd dimension. So we have these 3 resistances. They're in series. You sum them to get the overall resistance. And the overall resistance is not, I mean, we've done this before. It's just like that. Or you could express it as 1 over an overall heat transfer coefficient U. That's what we're introducing right here. Actually, I think it was introduced all the way back in chapter 1, but that's okay. Let's take a look here. It's 1 over U times A. Now at this point, you have the choice, and sometimes it's obvious what the choice is. It's like the area inner is the same as the area outer. So if area inner is equal to area outer, then it's just A, the same area. But if they're different, if area inner is not equal to the area outer, then really it's either 1 over U outer A outer or 1 over U inner A inner. The overall heat transfer coefficient depends on which area you picked it to go with. It's not that complicated, hopefully. But that can be a source of confusion to students. So just pay attention as to if they give you some size and they give you an overall heat transfer coefficient, those are usually paired together. Very rare that they wouldn't. Okay. Well, guess what happens if this heat exchanger has been in service and I have some sort of dirt, grime, grit? What could happen right in here after a long time? Some sort of film, some sort of deposits, and that would add to what we call fouling, fouling. It's not desirable. If you'd had fouling, how would you adjust the, you would put another additional resistance in right here, wouldn't you? Yeah. You would put an additional fouling resistance. Maybe I just try and sketch it like right over here. That fouling resistance, RF, what type of units does it need to have? Think about the 1 over HA. Remember that? What are the SI units of 1 over HA? Can I pause, let you walk around? I'm going to walk around. I want you to give me the units of 1 over HA. What is our thermal resistance? That has the same units as 1 over UA. That will have the same units as this resistance, thermal fouling, that I'm trying to get right here. So what are those units, SI units? I see a couple of us made it to the little picnic or whatever cook-off. All right, so either it's a degree C per watt or a Kelvin per watt. Why is it no difference? Why are these both good? Why are these both acceptable and not one wrong and one right? Well, because we're talking about a temperature difference. Temperature difference for that degree C. That's the same as a temperature difference in Kelvin. Okay, so this would be in units of degree C per watt, that additional resistance. Okay, well, let's jump to see how they describe it in the textbook. So they have this table for fouling factors. And they say, well, you have seawater and blah, 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 boiler feed water below 50 degrees C. Here's some fuel oil. Here's some refrigerant liquids. So, I mean, these are very highly dependent on how long they've been in service, what exact conditions there are. But they try to give you a sense of them. Take a look at this and look at the symbol. They put R double prime, don't they? R double prime. I prefer not to do that because what are the units on this? I would expect something like that to have units per meter squared. But because of the double prime, that's kind of the consistent notation. But this textbook, no. This is degrees C or Kelvin per watt, but instead of being in addition per meter squared, it's meter squared. So if I want that resistance fouling, remember just what I had on the other slide, R fouling resistance, what do I need to do to R double prime? Divide by area or multiply by area? Which is very confusing to students, so go slowly here. Because when I go back to the previous slide, this is equal to some R double prime F divided by A. Okay? I wish that would have been 1 over H fouling times A. That would have made sense to me. Some sort of fouling, instead of convective coefficient, some fouling coefficient in HF. But that they didn't do that, so just kind of get used to what's in the book. All right, there you go. So we have the overall heat transfer coefficient with fouling. There's our fouling on the inside. There's our fouling on the outside. When you look at this term right here, what do you think about? It's a tube. It has an inner diameter and an outer diameter, so we're trying to take into account that. Now look at, if it's a thin-walled tube, that term is going to drop out, especially if it's high conductivity. And then for the area on the inner, it'd be something like pi d inner L, or 2 pi r inner L for that area inner. And likewise on the area outer, pi d outer L. Okay. So again, this notation in the book has that double prime, and I think it's potentially confusing, so be careful. All right. Well, let's take a look at plotting a temperature distribution in a concentric tube heat exchanger. So we were introduced to that. We had a tube inside of another tube, and so often it gets a little confusing because I have maybe a fluid running here and I have a fluid running there and there. What we'll often do is just talk about the temperature of the hot fluid. Let's put this one in red, temperature of the hot fluid coming in, and we'll put the temperature of the cold fluid coming in. Now they're parallel flow, meaning that the inlet for the hot is on the same side as the inlet for the cool fluid. The direction of the flow, they're parallel. We're going to next talk about counter, opposite direction. Okay, so parallel flow conditions. So if I'm looking here, I'm plotting as a function of location from the entrance, let's put 0, down to location L, the exit. So that's how long the heat exchanger is. And we're plotting the single average or mean temperature of the hot fluid. Is the hot fluid going to get hotter, stay the same, or go down? It's going to go down, right? So it's going to go down. How about the cold fluid? It's going to get warmer. So the hot fluid's going to get colder, and the cold fluid's going to get warmer as it goes down further because of the heat transfer that's occurring from the hot to the cold, from the hot to the cold, from the hot to the cold. Can you get a heat exchanger where the hot comes out lower temperature than the cold comes out? Well, in this section, you would be having heat transfer from the cold to the hot. Makes no sense. It'd violate the second law. Cannot happen. Impossible. Right? So what's going to be the lowest hot out that it can go? The lowest would be the highest of the cold out. Maybe you had a super long heat exchanger. And then you think, well, this temperature difference, we've used the symbol theta, is going down, down, down. And that temperature difference, that local temperature difference, what drives that local rate of heat transfer from the hot to the cold, doesn't it? And so that Q local heat transfer is from 1 over U A, that local, maybe I just leave it like this, put a Q per unit area. Here, put it like this. U T hot local at that location X minus T cold at that location X. This is the Q at that location X. So at this location, I have a greater theta. So I have a greater heat flux pushing the heat transfer from the hot into the cold. But down here, I have a smaller theta, and actually, as you go further out from here to here, there's no more theta to drive the heat transfer. Negligible, no heat transfer at those sections. Looks like our old friend the exponential is going to show up, isn't it? Now, what I want to do is I want to set up really 3 equations. So we're going to focus on a little section, let's call this dx right here. dx, delta x or dx. And okay, let's all just say dx. Okay, and so in this little section, you have a heat transfer dq. True? And so we just wrote it over here. So the dq would be a u times an area, perimeter times a dx. That's my little small area, dA, times what drives the heat transfer, the temperature difference at that location. Again, I could emphasize that this is a low temperature at that location, the mean hot fluid temperature at that location. And this is the cold mean temperature at that location, and this is the little amount of heat transfer that's coming over that small area at that location. But the book, gets tired of all these subscripts, so it drops it like that lowercase x on that subscript. Okay, well, that's basically from this class. This is from a rate equation. You just can't get willy-nilly any U. It's governed by the boundary condition in the fluids, the thermal conductivity of the fluids, properties like that, or whether or not you have a high conductivity material or a low conductivity material for the tubes. That's the theme of this class, trying to predict from first principles convection coefficients and then model heat transfer, resistance to heat transfer, and overall convection resistance. Now, coming out of Thermo 1, energy is conserved. So out of Thermo 1, you have energy balance concepts. You've mastered those energy balance concepts. They still apply in heat transfer. So this little dq that comes out of the hot, it results in a rate of change of the hot fluid temperature as I'm moving down the tube. Let me try and describe that. That's like the slope of this line. Well, with respect to x, it's decreasing. The hot fluid temperature is going down as I increase x, as I march further and further down the tube. So what I'll do is I'm going to put a negative sign right away on that term. So I'm talking about a positive rate of temperature change of the hot fluid as it moves down the tube in the direction from inlet to exit. Okay, well, what you have is you have the mass flow rate times the specific heat of the hot fluid, and if you multiply by that little length dx, you pick up the actual temperature change of the hot fluid. Maybe it's a little hard to see at first, but this is nothing but an energy balance statement for hot fluid. Something came in, something came out of the hot fluid that was dQ. That's a positive so many watts of heat transfer. It results in m dot C times dt dx times dx. You do the same energy balance for the cold fluid. That's what comes in. Now the way I've written that, this is the same as that, They are all the same. What are they again? It's that amount, or the rate of heat transfer at that small area. Okay. Be something like in units of watts or kilowatts or something. Okay. So this would be the mass flow rate of the cold fluid, the specific heat of the cold fluid. So instead of putting m dot C and then C, I just say both of them are for the cold fluid, mass flow rate and specific heat of the cold fluid, and then the temperature change of the cold fluid with respect to X. Now in this case, it's as I move in increasing X, what is the slope? The temperature is positive slope there, so I don't need a negative sign. First time you see it, you think, oh, that must be an error because they have a negative sign for the hot fluid and they don't have it for the cold fluid. I just emphasize it. Look at the slope of those lines. And then we multiply by dx. Well, guess what you can do? You can work with your mathematical muscles and you can come up with overall energy balance statement for the whole heat exchanger. We're going to do that in detail, or at least show it, not for the parallel flow, but for the counterflow. They're very, very similar derivations. Instead of doing both, let's just do one. But before we get to that, in heat exchanger analysis, we often find the product of the mass flow rate and the specific heat of the fluid, both for the hot fluid and the cold fluid. Well, guess what they're going to do? They get tired of writing it, so they write cap C. This is somewhat confusing, but cap C is defined as the heat capacity rate. Cap C in this textbook. And it's very consistent throughout lots of heat transfer literature and heat exchanger textbooks, where the heat capacity rate is introduced as cap C. Let's take a look at the units. What would be the typical units of mass flow rate, m dot? Kilogram per second. What will be the units for specific heat? Oh, you know what? That's our first clicker question of today. What are the SI units for heat capacity rate, this cap C, right here? Is it kilojoules, kilojoules per Kelvin, kilowatts, kilowatts per Kelvin, or something else? All right, so everybody's in, right? So this game really is can you recall correctly the SI units of the specific heat? What are the SI units of specific heat? Something like kilojoules per kilogram degree C, or K, because this is temperature difference. So then we cancel out the kilograms, and then we say, what is a kilojoule per second? Isn't that the same as a kilowatt? Kilowatt per degree C. Well, we look down here, it's a temperature difference, same thing, again. So the correct answer is D. Okay. A lot of people went for kilojoule. Oh, they forgot that second, didn't they? That's what they forgot, right? Didn't pay. That's what they missed. Okay. So now let's talk about a temperature difference, concentric tube heat exchanger. And what we'll do is, I like to just typically divide it in half and say this is the hot side and this is the cold side, because it's really hard to draw a tube inside of a tube and then be meaningful. Just this is the idea. And so the hot fluid will come in here, temperature hot in. And if it's counterflow, guess what end the cold goes? Temperature cold in, right? And so that's the big difference. So here we're going to have temperature cold out, and here we'll have temperature hot out. We want to go ahead and plot the temperature. Maybe I have a line over here to help me draw the temperature accurately. And we have an inlet hot temperature, temperature hot in, put that high. Then we have over here the temperature cold in. The coldest or lowest temperature of any fluid in this heat exchanger is the cold in. The highest temperature of any fluid in this heat exchanger is the hot in. And then they'll have behavior. You could have something like the flow looks something like this, and the flow looks something like that. It could. Or there's plenty of different cases. You could have it where the sort of heat exchangers like this, maybe the hot is blowing through there so fast, so high a flow rate that it barely goes down as it flows through. And then the cold, it's just sort of dribbling along. It dramatically changes temperature as it goes through. You could have something like that. Or you could have something where the hot is just dribbling through and the cold is blowing through at a very high rate, or either high mass flow rate or high specific heat. That combination is your heat capacity rate. And so this would be a high. So C of the cold, the heat capacity rate of the cold, would be very much greater than the heat capacity rate of the hot fluid as I'm sketching it for this case. So the hot would go like that. Can you tell back here I didn't add that, but this is the heat capacity rate of the hot is much, much greater than the heat capacity rate of the cold. And guess what over here is? They're both about the same. The heat capacity rate of the hot is about the same as the heat capacity rate of the cold. Okay, I have another clicker question. So this one's a little tricky because which equation is not correct? So I'm looking for predicting Q. Is it m dot h, C sub p of the h, temperature hot in minus temperature hot out, temperature cold in minus temperature cold out? Which equation is not correct? Are any of these Q's negative? No. All of these Q's, the way we've written them, are positive. We're going to be trying to avoid negative terms for Q, okay? And so the whole thing is the mass flow rate times specific heat. Isn't that the same as this one right here? So these are, so the equation A and D look very similar, and the temperature difference is the same. So these are the same. And you look at it, you have the temperature hot in minus the temperature hot out. Temperature hot out is less, so this is positive right there, isn't it? Okay, then we have the mass flow rate, specific heat of the cold, mass flow rate, specific heat. These are the same, so it's something about the temperature difference. One of these is an error. Either B is an error or C is an error. New question. Don't choose A. Do not choose D. Which one is wrong, either B or C? All right, so let's take a look at our results. So some smart person decided A. When I said A, no, come on now. Somebody, either you miscued on your clicker or something, right? Okay, let's B and C, one of those is incorrect. Which one is incorrect? Why is B incorrect? Why is B wrong? Because the temperature difference, we're always talking about a positive temperature difference. And what does the cold do? It gets warmer. It gets warmer. The cold gets warmer. I know you have to work through it in your mind. It'll take a while. But the temperature of the cold out is greater than the temperature of the cold in. So we want to talk about this temperature difference. This is good. That one's incorrect. Should I go back and grade the previous? Nah, let's move on. Okay, I think if you could play this temperature game, you can really do well on the mathematics. The mathematics will follow, but a lot of times we get messed up in the concepts, and then the math just adds to the confusion. So this is a sketch of our counterflow heat exchanger. Temperature hot out, temperature hot in, temperature cold out, temperature cold in. Here's a sketch of the two profiles as I've shown. In this case, what can you tell me about the heat capacity rate of the hot versus the heat capacity rate of the cold? Aren't they about the same? Yeah, they're about the same. Look at the temperature difference of both of those. So this is a conceptual game. Now let's say somebody takes the same inlet conditions and they change the length of the heat exchanger. They make the longer heat exchanger. Can you see that? The hot is the same hot in, cold is the same cold in. What will happen to Q? What was Q? That's the rate of heat transfer in our heat exchanger. Will Q go up, stay the same, or go down? All right, let me do this. Let me kind of get this out of the way right here. We know that's true, and I'm going to extend X. And so X is going to come out this far, and this is about 2L. So I've made the second heat exchanger twice as long as the initial heat exchanger. And I come in here and I'm going to say, I'm going to bring in the temperature of the cold. That was supposed to be blue. Let's change it to blue. The temperature of the cold in is the same magnitude. Temperature of the hot in is the same magnitude. So if I tried to sketch the hot fluid in, would it continue along this slope and do something like that? No, it would do something like, it would change to something like this. It still has to come out higher temperature than the cold in. But it's probably going to come out closer to the cold in. So the temperature hot out probably is going to be closer to the cold in. And then this blue, it doesn't have the same slope as what it was before. No, that would be impossible. But like that. Okay, so temperature cold out. To see what's happening? You've given it a lot more area. It's like the fluid, each kilogram of fluid that came in, either hot or cold, it has more area to see for heat transfer to occur, more time it takes to flow through it. So what's going to happen to the Q? The Q is going to increase. I'm going to achieve a greater rate of heat transfer in my heat exchanger. Okay, I didn't say these questions were trivial, did I? I just said we got to play this game. So which window do we want to go under next? Do you want to just randomly take one? Like this is far right. Okay. Mass flow rate of the hot fluid. All the other inlets and conditions of the fluids are the same. It's only the mass flow rate of the hot fluid is increased. Then what will happen to the temperature of the cold fluid going out? So go ahead and work on that. While you're working on it, I'm going to go back and clean this up. And I'm going to put back that our regular length heat exchanger. And we have the temperature hot going like that, temperature hot out. And if you had super long, temperature hot out would be lower. Okay, so if the mass flow rate of the hot fluid goes up, what happens to the specific heat capacity rate of the hot fluid? Doesn't that go up? Yeah, that goes up because isn't that just the mass flow rate times the specific heat of the hot fluid? M dot of the hot goes up. Boom. So doesn't that make this red line sort of flatten out in the extreme? Let's say it really, really, really goes up. Doesn't it go like that? And what's driving the heat transfer? It's this theta. This is theta. A large theta over the entire heat exchanger drives the heat transfer. So what's going to happen, it's going to change the shape of this cold. It's going to be more like that, isn't it? It'll be more like I've shown. So what happens to the cold outlet? Doesn't it increase? I didn't say these were easier. Okay. Do you want to play another one? No? Okay, we have window 1, 2, 3, 4, 5, or 6. Number 3? Number 3. We go for number 3. U, the overall heat transfer coefficient, is increased. Will Q, then Q will increase, not change, or decrease. What will happen? All right, well, this one's a little harder to see, but just think about it. If U goes up, isn't it for the same delta T, a greater heat transfer. And so it's like, it'll make the blue line shift up. It'll make the red line shift down such that they seem to have the same slope, but a smaller overall delta T, a smaller theta everywhere, a smaller temperature difference, because you don't need such a large temperature difference to push the heat across from one fluid to the other. Good high U's make good Q's. So let's just take a look. Okay, well, it'll increase. All right. Do you want to move on, or do you want to stay with one more? We'll vote. Stay. Give me another one. We have 1, 2, 4, 5, 6 left. Or press on. Press on. Got a couple press-ons? Okay. We'll do one more. Now we'll take the number. Which one? Number 5. Okay. If L is increased, then the temperature cold will increase, not change, or decrease. If L is increased, you have a lot longer heat exchanger. What happens to the temperature of the cold fluid on the outlet? This is temperature cold out. All right, let's take a look. And what do we have? We have the temperature will definitely, of the cold going out, will increase. You have a longer heat exchanger, all the inlets and flow rates are the same. Very good. Ready to press on, right? So let's move on to something easier, Professor. Well, you think that's easier? Yeah, oh my God. No, back. Well, we have a derivation here. In the derivation to get an overall heat transfer predicted using the log mean temperature difference. So that's what we're going to derive. So you can derive it for the parallel flow, you can derive it for the counterflow. I've done it for both. I just threw one of the derivations out. Let's only look at one of the derivations. It's long enough. If you were the first to do this, never saw anybody's notes, never saw anybody's outline of how they did it before, you would probably spend more than a few days on this, because it can be a little tricky. But here is kind of like hot knife through butter, like, wow, that was pretty clever. Why did you do that? But hey, it gives us a solution in one page. So we have the definition of the heat capacity rates. We have equation 1, equation 2, and equation 3. This comes from an energy balance, only focusing on the hot fluid. This comes from an energy balance, just out of thermo 1, looking at the cold fluid, just a small little dx and the fluid flowing in and out of it. And then this is for the what? The rate equation, basically like a combination of Fourier's law for the conduction through the wall and law of cooling for the convection. That's a combination. If you had fouling, you'd put it in there too. That's this class. This class. The others are Thermo 1 background, prerequisites. Now, why do we have two negative signs? Well, when they are counterflow, both of those temperature gradients are negative in the positive x direction. Okay, so you take equation 1 and 3 and equation 2 and 3, you get new equations. You can get rid of the little dx. You add those equations, or take the first and then subtract the second from it. And you combine them algebraically to get this new equation at the top. You recall from an overall energy balance that the overall Q is this, overall Q is that. You take a look and you say, well, then I can replace 1 over the heat capacity rate of the cold by this ratio, and the 1 over the heat capacity rate of the hot by this, put them in here. Then you simplify with some algebra, get a differential equation. At this point, it's like you can separate and integrate. I really didn't get to the full, I guess I did. Here's the differential equation in terms of temperature difference. The space derivative of temperature difference, proportional to all these are just constants times the local temperature difference. Separate and integrate. Apply the right boundary conditions, and then you manipulate algebraically, and you get a rate equation for the overall Q, which is correct that it satisfies both energy balances, but also the rate at which heat is transferred, controlled by the convection and the conduction resistances. It's equal to UA delta T2 minus delta T1. Delta T2 is maybe on that end, delta T1 is on this end, divided by the natural log delta T2 over delta T1. That's UA times delta T log mean. That's a very simple equation with a long derivation. So you'll have this equation, Q is equal to UA delta T log mean. Let's solve a problem. We have a counterflow heat exchanger. Maybe you want to sketch that, maybe not. Let's just sketch it like this, divide it. We'll put the hot fluid on one side, the cold fluid on the other side. Okay, since it's counterflow, if you're going to bring in the hot on this side, you need to bring in the cold on the other side. True? So let's start putting in our temperatures. So we have the temperature hot in is 90 degrees C. The temperature cold in is equal to 40 degrees C. Okay. The mass flow rate of the hot is 2 kilograms per second. So maybe I put up here m dot hot 2 kilograms per second. And the specific heat of the hot, C of the hot, is equal to 4.2 kilojoules per kilogram Kelvin. Okay. Cold, I can do the same thing. Actually, you can now take the product and get the heat capacity rate of the hot and the heat capacity rate of the cold. Heat capacity rate, 2 times 4.2, let's see, that's 8.4. Then we're going to have kilowatts per Kelvin. And then whatever it is for the cold fluid, 3 times 1.8. 3 times 1.8 kilowatts per Kelvin. Okay, so I've kind of read through this information. Now this information, they're giving us the area, how large is that heat exchanger, and then the overall heat transfer coefficient for that heat exchanger. And notice this was in units of watts per meter squared degree C. Okay. Determine the cold outlet temperature. And you're not supposed to know the answer, but you're going to get the answer of 72.6. That's the final answer. Likewise, what's the hot out, log mean temperature difference to the heat exchanger, and the Q? So, how in the world do you solve this problem? Well, there's a couple of equations. The equation would be that the rate of heat transfer out of the hot fluid is the heat capacity rate of the hot fluid times the temperature of the hot in minus temperature of the hot out. Is that good? Energy balance equation? Sure. Let's do this. I like to put a little check. Do I know that term? Do I know what the value of cap CH is, which is the heat capacity rate of the hot fluid? Yeah, it's right there. Do I know the temperature of the hot in? Yes. Do I know the temperature of the hot out? No. Do I know how much heat is transferred in this heat exchanger? No. I have 2 unknowns, 1 equation. I don't care how long you work on this problem. Bang your head against the brick wall, look for another equation. So we get another equation. It's Q for the cold. Heat capacity rate of the cold. Temperature. Is it cold in minus temperature cold out, Professor? Or cold? Yeah, we already did that game, right? It's cold out. That's the higher temperature than cold in. But then I say, I know this one. I know the temperature cold in, but I don't know this one. But these 2 Q's are the same, so I'm not going to put a subscript on the Q's. So, but I have 2 equations, but how many unknowns do I have? Well, I have Q as an unknown, temperature hot out as an unknown, and the temperature cold out as an unknown. So I've got 2 equations with 3 unknowns. Can you solve that? Maybe you're a really clever mathematician. Can you solve for 3 unknowns with 2 equations? No. Unless it's some special case of some mathematical something. But no, it's not. Right? This is just engineering. We need another equation. These both came from Thermo 1. We got to have something new for this class. What's new for this class? Q is equal to UA delta T log mean. That's what's new for this class, the concept of resistance, thermal resistance, and rates of heat transfer and convection and conduction through the wall. That's all embedded in this big U. All right. Oh boy. So what is my delta T log mean? Well, I'll talk about this delta T on one end, and then this delta T on the other end. And then that log mean temperature difference, I could rewrite this equation as UA delta T1 minus delta T2 divided by the natural log of delta T1 over delta T2. But basically the discussion ends right there. Now I have three equations, three unknowns. Let's put on our mathematical hat, forget that we're engineers, and solve the problem. We've got a nasty mathematical problem of three equations and three unknowns. How are we going to solve it? Set up a matrix AX equal B if it was all linear. Are these linear? Look at the log mean temperature difference. Not going to happen. If the energy balances are nice and linear, but that log mean temperature difference is the problem.
Can you combine the first two, set them equal to each other, and then just sort it so that you have THI minus TCO on one side? And then
There are some people who did like you did, and that's called the effectiveness NTU method, and that's going to be a real derivation when we derive that and talk about just a little bit of work to derive the log mean temperature difference. We showed that. We are talking about a lot of insightful manipulations to get the effectiveness NTU method. But at this point, if we're sticking with the log mean temperature difference method, I'm looking for something else other than what you just described, which I'll say is going in the direction of the effectiveness NTU method. Let me give you a hint. My favorite little thing in the playground when I was a child. This merry-go-round. You got to just jump on, friends. You got to guess and iterate. And that's common. That's just common. That's not that hard. We should be comfortable doing that. So in this idea, it's like, you know what? I could sort of guess a temperature of the outlet, one of the outlet fluids. That's what we're going to do. So in the interest of time and everything else, let me kind of set up here. I just said for my first iteration, I'm going to try and draw it down here. Come down here. I'm going to put like right here. Okay. Let me put it in this order. I'm going to take and guess that, because it really just, you merry-go-round, you just got to get on somewhere. Guess the temperature of the outlet fluid. And the first time I did this, I guessed that it was 60 degrees C. What does that allow me to do? When I look at this equation right here, it allows me to calculate Q, doesn't it? And so all of these have units degrees C. I don't want to keep writing the same units. But if it's, let me do this. I'm going to pause. You tell me if the temperature outlet is 60 degrees C, what is Q? Give it to me, please, numerically. So we got that this was in kilowatts, Q, and it was 108, true? And then we were able to get the temperature hot out in degrees C, coming back to this equation, right? So it's like guess this, use this equation to get Q, then use this equation to get T hot out. T hot out came in at 77.14. Then we went and calculated the delta T, or log mean temperature difference. Log mean temperature difference. This ratio, I do that as an intermediate step, and it was 33.44 degrees. Then I calculated Q from the rate equation, this Q right here. That Q. This Q came from this equation. But this Q is from the rate equation, and you get 258 kilowatts. Now, I can take a look. Is 108 and 258 the same? I didn't have a very good guess. I need to revise my guess. How am I going to revise my guess of the cold outlet temperature? I'm going to go back to this equation, and I'm going to say the Q is 258. So on the second round, right here, it's kind of like we're starting with now. Q is 258. Can you give me the new best estimate of T cold out from this energy balance equation of Q is 258? Can somebody calculate it, then call it out for me? 87.9. If you think that's too far, which it is, then back up, because sometimes these equations, when you guess and iterate, it becomes nonlinear and waffles around. But you could just, continue to adapt. Maybe only go half that distance or something else. But if you go to where you find that the temperature is 72.6 degrees after a few rounds of iteration on the outlet temperature, then this energy balance for the cold fluid will predict that it's 175.98. I'm giving you too many digits on it, but this is the final answer after a few iterations. And then the top temperature hot out is 69.05, and the log mean is 22.74. And then the final rate from the rate equations, 175.98. Hey, that's it. They converged. So we're done. So the final answer is, hey, 72.6, 69.05, 22.74, 176. Okay, too many digits on this one. Does that make sense? You have to solve a problem on your own. Let's see, how much more time do we have? Let's cover this topic. I want you to calculate the log mean temperature difference, when delta T1 is equal to delta T2. Well, what's the definition? Delta T1 minus delta T2 divided by the natural log of delta T1 over delta T2, right? So you say, hey, if they're the same, then this numerator is 0, and then I divide by the natural log of 1. Mathematically, your calculator will not like this. Put in the natural log of 1 and then, reciprocate. What are you going to get? 1 over 0. Blows up. Infinity. Math don't work. Don't trust anything in this heat transfer book, period. Well, no. What you have to do is you have to basically sneak up on this problem. Think about it. If delta T1 is equal to delta T2, basically the log mean temperature difference better not blow up. It better finally give us the answer that the log mean temperature difference is equal to that temperature difference on both sides, inlet, outlet, and throughout. So what you do is you do use L'Hopital's rule. So maybe the textbook you use, they call it almost like L'Hospital's rule. L'Hopital's rule. This class is not hard. It's the prerequisite math and the prerequisite fluids and the prerequisite thermo. True? L'Hopital's rule. So if you're trying to take the limit of f of x divided by g of x, maybe as x goes to some value, I can pick 0, but they can pick a or a constant, something else. And the limit as f at x goes to that 0 is 0, and then the g, it also goes to something like that. Well, then you need to replace the original problem with the equivalent problem that I'm going to take the derivative of f prime divided by g prime, take the limit of f prime g prime as x goes to 0. That's what you have to do. So in this problem, what we do is we say that delta T2 is just our delta T, and then delta T1 is delta T plus a little bit. And we're going to let epsilon go to 0. So what happens is you've got the log mean temperature difference is equal to the epsilon over the natural log of 1 plus epsilon over delta T. All right, so now if I put in 0 there, I have the problem. So we don't do that. What we do, if we want to take the limit as epsilon goes to 0, we basically replace that by the limit as epsilon goes to 0 using L'Hopital's rule of the derivative of the numerator with respect to what's going to 0. So the derivative, here's the easy one, derivative of epsilon with respect to epsilon is 1. All right, the harder one, the derivative of the natural log of 1 plus epsilon over delta t, all of that as with respect to epsilon. What is that? That one's not so easy. That's 1 plus epsilon over delta t times 1 over delta t. Now, if you let epsilon go to 0 of that, this term goes away. Then we just have in the numerator 1, denominator 1 times 1 over delta t. The whole thing just flips and you get delta t. It's like what we would have expected not knowing any calculus. So there you go. Well, with that, I see that I'm out of time. There's some more that I want to say about the log mean temperature difference approach and predicting Q is equal to UA delta T log mean. But hopefully next time we'll get into the effectiveness NTU method. Thank you so much for your attention.